Hello. How is the volume on the mics? Can you hear me all the way in the back? We good? Okay. I'm Angela Metler. I'm an administrative assistant in the president's office at South Dakota Mines, and this is Steam Café. Welcome. We do this every third Tuesday. Steam Café is a partnership with... We will not have these two on at the same time or be really close to each other. Steam Café is a partnership with Hay Camp Brewing and South Dakota Public Broadcasting, so we thank them for their support, and we thank you for your support as well. As usual, we are broadcasting on Zoom tonight, and if anyone is watching on Zoom, thank you for coming as well. At the very end of the presentation, we'll do a Q&A. Obviously, questions can be asked live by the audience. Anybody on Zoom that wants to ask a question can either type it into the chat or into the Q&A box, and we will make sure that it gets answered live as well. Yeah, I think that's it. So, brief introduction of tonight's presenters, Dr. Katrina Donovan and Dr. Haley Armstrong. Take it away.
All right, can you hear me okay? Wonderful. Thank you all for coming tonight. And again, thank you to all the sponsors to making this happen. I'm really excited about this talk. So I am Dr. Haley Armstrong, Director of Bands and Coordinator of Musical Activities out at South Dakota Mines. And Dr. Katrina Donovan is a Senior Lecturer in the Materials and Metallurgical Department, also at School of Mines. And this project has now been 2 years running, and it's neat to get to share it with all of you and get your questions and feedback. So we're calling this Metals and Music, Arts plus Engineering Applied to Musical Instrument Design. And how it began is in spring of 2023, I was asked by the South Dakota Bandmasters Association, which is an amazing organization. You can kind of read about what they do, but they promote excellence in music, and they have a conference every year. And often the music schools will play at this, the colleges will, talented high schools will, but School of Mines had never been invited because we don't have music majors, we don't have music minors, and we got invited. So this was my wind ensemble, which we'd been working with really hard. And so you can see on there that they were interested in doing excellence in music, which our students do. They're amazing. But I also wanted to showcase some of the excellence and uniqueness that I see at School of Mines every day. One of the things I love about this job. And so this was my 8th year at Mines when this all began. And just if you don't know much about our music program, here's a little just quick facts. We're part of the South Dakota, South Dakota Mines Humanities, Arts, and Social Sciences Department. So we encompass a lot of different disciplines in there. And the music department right now has over 310 members performing in 9 of our ensembles, even though you would think that this is like extracurricular, but it's not. They're taking these curricular classes. The students are extremely dedicated, even though we have no music majors or minors. That's about 12% of the campus right now, because if you think about it, all the really smart students also were the band geeks and the band nerds in high school, and I see some of them out there. And it makes so much sense, and this is why I love my job. And we have students from every major representative. We have master's candidates, we have PhD candidates, we have faculty. And so I decided if I want to show off the school, I'm just going to ask my students, hey, I really want to do this piece. Do you have any ideas on things we can do to make this special to us? And so this was students, their organizations, their own creativity, nothing formalized, and here's what they came up with. Composer John Mackey writes in his foreword to his piece Foundry, quote, "The idea with Foundry was to make a piece that celebrates the fact that percussionists have the ability to make just about anything into an instrument. It won't end up surprising that Foundry for concert band with found percussion, much of it metallic, ends up sounding like a steel factory." Now, this spoke to the uniqueness that I see around me every day at South Dakota Mines. Here at SDM, the students are extremely smart and driven, but they are also creative and deeply fascinated to learn how things are made and how things work. For our performance, I reached out to some of the classes and professional organizations on campus to see if they could help us create our instruments for this piece. My first step was to go to our own South Dakota Mines foundry, which houses multiple STEAM groups, including blacksmithing, casting, and welding. The highlight of this experience is when the foundry hosted myself and all of our percussionists to forge our own triangles. None of our current percussionists are metallurgical majors, and so it was a new experience for all of us, learning how to bend and treat metal to produce functional and beautiful sounds. We also had diverse teams design our PVC pipe marimba and our 3D printed wood blocks. They all have a love of art and design. Now, is some of this a bit over the top? Yes it is. But I'm so proud of these student-driven design projects, which helped our whole group think about music in new ways. Similar to the way that continuing to be involved in music and the arts while studying STEM helps students think creatively and innovate new solutions to problems in STEM and problems in our society. Hopefully Mackie would appreciate our version of Foundry, and we hope you enjoy our performance. All right, wasn't that cool? And so that was all student projects, like the guy that designed the drone to drop the marbles on the cymbal, which, yes, he got 2 of them. The first 2 did bounce. He was just like, yeah, I can do that. Sure. The funny part was, the reason we had this video is because SDSU would not let us fly a drone in their auditorium. I know. So then, how is it going now? So that project, which was just me and the students kind of having fun, turned into this. So the MET 352 Principles of Metallurgical Design course is taught by Dr. Donovan. And this is junior year in the spring, about 20 to 25 students normally. And they divide into groups, and they're tasked with casting, forging, glass this year, ceramics, different manipulation of metals. And in the past, they had done just all kind of different projects. And then she came and asked me if I would be their customer and have the bands, the music we were going to play in the spring, they have to develop this. Now, these aren't music students for the most part in these classes. But the most important part I want to say that I'm introducing this because she won't brag about this. These are the faculty advisors that help with these groups. You have the department head, you have full professors, the passion that they get from a junior design class and how much hands-on help and just worlds of knowledge. This class is just so much fun. So I'm down here and I'm so happy to be on this slide because it's just like I get to hang out with these people and learn all the cool stuff they have. And so our first year we did this was after the February performance. Same semester was spring of 2024. And you can see around the room, we have some of the instruments you just saw being performed, but here was the next iteration, which included all of these major professors and the science backing it.
At South Dakota Mines, we run on the motto, build it, break it, create it. A perfect example of this is from the spring 2024 Junior Principles of Metallurgical Design course. In this course, students are challenged to use system engineering principles, teamwork, project management skills, technical communications, and material and process selection as they relate to metallurgical engineering, and this semester, as they related to their customer, South Dakota Mines University Band. 5 teams set out to create new instruments for this performance in their assigned medium, either forging, casting, or ceramics. Guided by the faculty advisors, they needed to combine the art of design and creativity with the science of their materials and the methods to deliver a final product for our performance tonight. There were 2 forging teams. One settled on creating a cymbal, and then the other on a set of chimes. There were 2 casting teams. One created a post horn, and then the other created a set of carillon bells. Then there was 1 ceramics team, and they created 2 traditional drums. For each project, prototypes and molds were created and materials were tested. For the post horn team, they only used recycled materials. And for the ceramics drum team, they created their bowls out of Black Hills clay they gathered themselves off of Tower Road. Now, this project wasn't without its challenges. Air conditioners destroyed curing clay. Casted metal had a mind of its own. And luckily, these students took their jobs seriously, testing materials, creating safe environments. We are happy to report that all teams were successful in creating a product that then was explored and manipulated by the musicians performing tonight. This was a true teamwork from creator to performer. It is amazing what our students can accomplish, and we hope you enjoy hearing these new instruments on our performance of Randall Standridge's Celebration Tribalesque.
All right, so that was 2024, and then this spring, we did it again. So I'm going to turn it over to Dr. Donovan to talk about what happened this semester.
Thank you, Dr. Armstrong. And I think on her slide, she should have been much higher up there. She's a pretty key, I feel like I'm pretty echoey, key component of this The students are always going in asking questions, so we're very fortunate that we've been able to work with her. I might stand on that side. That seems less echoey. Is that less echo? No. Let's do that. Is that better? Awesome. Yeah, I couldn't have listened to me through that either. Once again, thank you, Dr. Armstrong. We are really fortunate that we've been able to work with her the last 2 years. It's been so fun, and the students have had just the opportunity to have a different perspective looking at a problem. And I really wanted to shout out all the different instruments we've made this year. I don't have the time to talk about all of them. I'm going to be talking about 2. I'll be talking about the ceramic flute and then the glockenspiel, but there was a lot of really cool projects that the students did, and I'll dive right in. So when we start with the design project in metallurgical design, we start with a problem statement. This first one we'll do is the glockenspiel. The problem statement is similar if you're more familiar with science. We start with a research hypothesis. In engineering, we start with a problem statement. Engineers, we're problem solvers, so defining the problem or what we're going to do is really where we start, and that's what this group did. So the glockenspiel is actually this one right here. They designed and produced 13 glockenspiel keys. They went through a casting process, and then there was a couple different songs this year they could design their instrument to align with. This one specifically went with Roma, and then there was 13 keys that they made. As you notice, there's not 13 keys. The other half of it's in a display. I should also say, as I go through these slides, you might start noticing there's 2 different slide decks. It's because these are all student slides that I'm presenting. So you'll be as surprised as I am with each slide. No, but I really wanted to shout out the students. These are all student slides. I didn't modify them. I'm just helping tell their story. The other thing we want to keep in mind is a stakeholder. In this case, it's Dr. Armstrong. We give the students constraints. We tell them how much money they can spend, because I'm sure if we gave them $20,000, they would make an amazing instrument for us. We're not quite there. We're about $400, so there's definitely a sustainable loop in there. But keeping the customer in mind, there's a lot of instruments that we could make, but it might not align with the song. So that was one thing to keep in mind. From the material science background, this is really where I want to start with this team. So they did a casting. When we cast, we're going from a liquid state into a solid state. So they needed to heat up the metal. So there's a couple different furnaces they looked at. We have an electric furnace, which is about 1,000 degrees Celsius, gas fired, and then the induction. They were able to use the electric furnace for this particular design. And I really want to actually point out this next one, the safety one. It's the brass casting. One of the things we really encourage the students to do is to go talk to Dr. Armstrong. One of the things I also encourage them to do is talk to the year before. Is there anything that you can be learned? And this group went and took the time. Brass casting is a fun one because you have zinc in there, and so it's zinc fever. So the fumes off of that, the particulate you can inhale it. So it was the year before, they spent about 4 weeks just trying to get the safety guidelines. So we in no way skimp on how we're doing these processes. This group was, they were smart engineers. They learned from another engineer's mistakes, and they decided to make different design decisions along the way. So they decided to go with an aluminum, easy to grind, easy to cast. They also chose a specific type of aluminum. The aluminum they used is from recycled cans. Of course, I joked, college students, recycled cans. If it was my era, it would have been one type of soda cans. I was very surprised. I went and looked at the cans they had. These kids are Monster drinkers. These are energy drinks. There was a lot of Monster cans that went into the making of those glockenspiels. But they stuck with the same can design throughout, melted them down for this. So just some considerations they had during this process. The other thing is when we're casting, there's 3 different casting methods they really looked at. Sand casting, which is what you can see on the right-hand side. You take a sand mold and you can press into it. Lost foam, it's a non-permanent mold, non-repeatable, so they'd have to do this multiple times. It's harder, in this case, to get the required precision. Then they also looked at a permanent die cast. That's usually expensive, time-consuming. Very effective though. And then they also looked at mold design for a lot of the 3D prints, which I'll show you here in a second. The construction for this, they're rectangular bars, as you can see right there, generally made from steel. Steel has a higher melting point than aluminum. In aluminum, we really wanted to keep this recycled sustainability component, so they stuck with aluminum, but could learn from what was done with steel here. And then the harmonics, I'll get into those a little bit later, but they wanted to keep those in mind. So frequency is directly proportional to both the thickness, and then it has an inverse squared relationship with the length. So if you want to change sound, and we'll get a little bit more specific, you can either trim off the edges or trim like through the thickness of it. And by trim, I mean grind down. So here's design requirements. This is a really important part of design, is being very specific on what our customer needs. So in this case, their requirement was the ability to tune keys. They selected 13 keys, that was their goal. Must be loud enough to be heard by the audience. It's kind of important. If we can play it and only I can hear it, it's not a very useful instrument for Dr. Armstrong. Bars must be machinable. That's a big one. When we're doing a lot of casting, there's often what we call post-processing. So it's not like it comes out perfect. We have to do things afterwards to get it to an appealing look, or maybe even to get to the sound we want. So the machinability is a very important part. And then the other requirement was it must be able to be played by a percussionist. Once again, the percussionist can't play it. It's not very useful for Dr. Armstrong. One other thing we really walk through with the students is we as humans might have gut feeling. Gut feeling is not very quantitative. As engineers, we try and quantitate that as much as possible. So here, what we have is what we call a trade study. And so this, we'll just stick with table 2. You can read the bottom one, but I'll walk through a table 2 example. It's the casting method trade study. So they have the different types: sand casting, investment, lost foam casting, permanent die casting. And then they looked at a variety of different things: porosity, impurities, mold design, repeatability, cycle time, post-processing. And then they added a weight to each of those. How important is it? Can we get over that? And then they weighted each one. So if you see, like for sand casting, you can see the score and then the weighted score. And you get all the way across, and you can see here, it got a 56 for the sand casting by totaling all these different variables in there. So a common thing we do in design these trade studies, they help kind of quantify that gut feeling. I think they kind of had a feeling we'd probably end up with sand casting, but really putting numbers to that is an important thing in engineering. Another framework we give students is a flow. Where are we starting? Where are we going? I think one of the most important parts of engineering is that feedback loop, and you can see a couple different ones here. With this particular one, they started here with the CAD pattern design, and they worked left to right. And when we got to the sand mold, that construction, they did a melting and cast. So they melted their metal, casted it. They had a bad cast. They needed to go back and redo that. If it was fine, we went to machining. And then did testing and tuning. With the testing and tuning, if it wasn't the way we wanted it or needed it, we might have gone back to the sand mold construction, or we might have tuned it and put it back in. But as you can see, these different loops in the process, and we'll show you some examples of those. Once we got past that, you get to the final product. For the tuning and testing, they often use a lot of different apps, either on your phone or Dr. Armstrong had ones they could use. Safety, I kind of talked about that a little bit earlier. We pulled these slides, they didn't come through clean. This says design safety. Some of the things to keep in mind: molten metals. The molten metals they were dealing with were above 600 degrees Celsius, so they're quite warm. We have flammable gases that we need to consider, hot tools, and then also toxic gases if you're working with like brass, so zinc can come off, lead, those are all issues. They didn't have that, they were working with an aluminum, there wasn't those in them, but as you can see, they're still PP'd up, PPE, so personal protective equipment, they're still in that, and they're not having any fun. They were totally miserable, not having any fun at all. No, I think the funnest part was just to see the groups get together and really get to interact in a hands-on way. So they had a good time with a lot of these. There were struggles, but definitely had a good time along the way. So for final selections here, they chose a modeling and a printing. If you look at the blue part, that's a 3D printed part at is it the stage that holds it together? Stand that holds it together. See, this is why I'm lucky. The stand that holds it was 3D printed, and the molds and shapes that they used for the casting was also 3D printed as well, and then used to press in there. Casting equipment, they used a propane-fired furnace, tools, some other things they had to use afterwards, grinder, belt sander, did some hand sanding to get down to that fine tuning. In terms of the tuning, I kind of talked about this a little bit. There's a couple different tuning apps. Dr. Armstrong has equipment you can use as well to tune. But for the glockenspiel, this is actually, I think, modified off of a xylophone. A very similar instrument was where this literature came from. But you can see here, if we remove material from this end or this end, it will sharpen both the fundamental and the overtone. And then if we move from the middle, so not shaving off the sides, but from that more center, it will flatten out the fundamental note. So what that means, lower thickness, lower tune, lower length, higher tune. And so we were able to, the students were able to do 13 different notes with this and get within 3 cents accuracy. So I'm told that's really impressive. Frame assembly, I'm gonna kind of fly through this real quickly. You only got part of it here. We got these ones here, but they 3D printed these. They had lower and upper frames. They had felt pegs, so they designed all of these. And then plywood, like for a stand. One of the big parts of this is, for example, I'll pick on this gong. I know I'm not talking about the gong, but it's probably, easy to make a gong, but that's not good enough. If we just hand Dr. Armstrong a gong, she's then got to build a stand for it. So part of it is it's not just making it, it's making it functional and useful and actually helping that whole process. So making it wasn't sufficient. It had to be like made and functional to completeness, or we could hand it off. So some results are the property tests that we did. So for this group, they did 4 different tests. They went and looked at composition. So they used X-ray fluorescence to do that, and that's what we see here. So a big portion of their aluminum was, as you'd imagine, aluminum. It was 90%. But you can see some other things in there, some magnesium, a little bit of copper. But for the most part, it's aluminum as we anticipated with using an aluminum can. And then we did see a slightly high silicon content and then just some references they had. They also did hardness testing on these, so Rockwell B test, and they got 59.4 and 48.2. I think in a slide or two, I'll talk about that. And those, we were really looking at mallet strike zones. So there's different parts that the mallet hits as well. They also did a drop test. So if they drop it, we don't want it to shatter. Not that we'd worry about that with metal. We did have other instruments that was a concern. But they did drop it from 5 feet high. They only got a small dent. So even if something happened during transport, we were probably okay. Porosity, that was a huge one that the students wanted to go and investigate. We have curious students, we have creative students, but we also have curious students. And so with the porosity, at one point, I remember this group, they really wanted to go and investigate that. And part of design is, we've got a product. That's a great question for a scientist or maybe a summer project, but they did a really good job on really asking a lot of good questions and identifying things that could be fixed in the future. Part of being an engineer and solving a problem is also saying, how can I improve upon problems that exist? So they really wanted to dive into that. We calmed them down a little bit, but it was kind of a fun path they about went on. Some challenges they really did have. Broken bars, that's pretty common sometimes with a cast that happens. Time, the belt sanding was a very slow process for them, as well as the angle grinding and the low grit belts. And then tuning, we see temperature affects the tune. We saw a 10-cent variance, and then they had to work on adjusting the tune. And then, like with this one, there were a couple recasts they had to do. So 13 keys was pretty ambitious. I'm just gonna kind of high level go through this. They went through some discussion about different recycled cans, tuning, and then the different tones the bars could produce. And one of the big things a lot of these teams kept in mind was low-cost casting and machining, so what's around that we can already use in a sustainable way. And some recommendations. I'm not going to go through all the recommendations, but that is another thing as an engineer. What is that next thing we can improve upon for that next cycle? To be clear, this is a lot that we give them 15 weeks in a semester, and part of that is just learning engineering design, getting these terms, what is a problem statement, a constraint. There's all of this in this whole time. Some of the students have never cast before, so they're learning this whole manufacturing process. And we're grateful we have Dr. Armstrong, but we're also learning music a little bit along the way too. So there's a lot of moving parts in there. Standards, I just wanted to keep this one up here. We're always following some form of standards, whether it's safety standards, which you can see here. If we're looking for aluminum die casting standards, there's a lot of standards out there, and we really align with those as much as we could. And they did a great job. They stayed under budget by quite a little bit. So $370 under budget. They were supposed to be $400, so they did really well. They only spent $30 on the project. The next one I'm going to jump to, is the flute. They also start out with that problem statement. We like to identify who, when, what, and they also have the requirements and then also some restrictions. Restrictions, you, like I said, can think about constraints. I'm going to go through some of like the traditional engineering stuff a little faster because I talked about it already. But for this group, they were with the flute, which is right there. I guess I should have you play it, huh? So this group, they made a flute. They also made the mutes that you might see. Almost. It is a weird mouthpiece. It was the first 3D printed one we had with clay. So it's kind of... Yeah, there's a mouth. We did add a piece to the mouth part of that to help it. But they started with 100% local minerals. So they went to a place, it's our little hidey spot where we found a pretty good clay body that works geologically. So they had to mine it. They then took it, they dried it. They went through a grinding and a sizing process. They did what's called XRD. So XRD is X-ray diffraction. So you can take a mineral, hit it with an X-ray, and the way it diffracts, it can give you information about what minerals are in there. And it'll also give you, like here, quartz, shows you also the percentage of them. So from XRD, they could formulate a clay body that they could then 3D print. And here's their flow chart. So they started with a collect, and then they went to a process, and then they printed, and then if it failed, they had to rehydrate it and reprocess it to print it again. If it printed and it was good, they went to the drying cycle, where they'd where they dry it, and then this is the firing cycles they went through. I'll also talk about raku. If you're a pottery person in the audience, you probably know quite a bit about it. If you look at this particular design, on it you see all the black. I don't know if you can see it. So they put things like horsehair and grass when they fired it, and so it really makes a really unique design. So that was something kind of unique they did, and they had to kind of do we're not really set up to do that particular part, so they set that up to be able to do it. And then they tuned it, sealed it, there were some leaky spots, and then it was able to be played. Here's their decision matrix. A couple things they looked at was the tenor flute, or a chime, or a xylophone. We had 3 glockenspiels like that for this group, so I think part of their design was not being like, design choice was not being like everybody else, and then a couple different clay bodies that they looked at that are in the area. For this one, they really had to dive in for a flute calculator. And so this was from the Bracker whistle and flute hole calculator. So they wanted to look at resonating frequency of pressure oscillations within a column. And then we had to keep in mind different vibrations, column lengths, different frequencies. And then some other physical criteria they had to look at was tube diameter, wall thickness, flute total length, and then hole shape, hole size, shape, and position. And those are all different things they could put into this, and it would help guide where they should be putting the different pieces. And actually, I think because of the limiting size of our 3D printer, they had to actually print this in 2 segments at one point. So here, I don't know if this will play or not. So that was like trial version 1 with just a PVC pipe. They also started with a commercial clay. Commercial clay is already ready to be used in a good starting point for learning how to run a clay 3D printer. Clay 3D printer works a little bit different than a traditional polymer 3D printer. Just do a quick raise of hands. Who here has a polymer 3D printer? I've done some stuff. Okay, a couple of you. The unique thing about a polymer one is you can pick it up and move it everywhere. This one, it's like it's either on and going, or there's no like stopping it. So there's no picking up. So they really had to think through the 3D printing design part because there isn't a stop or a pause per se in that. The other thing they did is they did do a series of different flute tubes that they worked on, but they also did some different testing as well. So this is an example of a 3-point bend test. We have our, it's just a very long rectangle, 3-dimensional one, and then they're applying a load here on it. So you can see the 3 different points, that's where it gets its name. This piece was fired to a low cone fire, about 1,000 degrees Celsius. They also did a measurement for a shrinkage factor. That's another thing to think about. If they're 3D printing, we just talked about how important the flute diameter is for a lot of the fingerings for those. They had to think about shrinkage factor for that. So they also use that ASTM as well. Here's also some of the printing. You can see some fun challenges they had along the way. So they had air pockets would tear holes and dimples and things. They had a clogged nozzle. They call this an elephant's foot. It caused some challenges there. And then just setting it up, there's a lot of weight on that clay. And so that was its own challenge with warping and partial collapse. I think at one point it was named the Tower of Pisa because we had some printing challenges there. As you can see here, it was a little bit leaning. So a lot of different things they did to work through that. Geometry changes, drying fans. Can we have this dry and stiffen up while we're printing the rest of this? So they ran into a lot of challenges. I asked the students if they saw how I handle parenting with the duct tape and against the wall. No, I'm just kidding. They're like, it did work really well. So that's actually one of their ways of, they did have some challenges with that slumping on the side, but they were able to tape it to the wall and that really helped support it. So for all methods, it was necessary to cover the tubes for drying and cracking. So you did have different rates of drying as well with, as these were being printed as they changed that. Hole manufacturing, they did a lot of different things to get to the holes. This is just a flat 3D printed piece, and they really wanted some high resolution. So this was a laser engraver. It took a long time to get the one and only hole they had, and they're like, that's not gonna work very well for us. Another option was pre-cut, so leather hard. You can have shrinkage compensations. You get, they were able to have some shrinkage compensations, so I think they ended up going kind of a little bit between these two with the subtractive bisque drilling as well. So they were able to cut these out before they fired it. When they fired a couple of them, after they were fired, they were a little bit too brittle to work on some cases, and then the bone dry, we had some collapsing. So after they put these guys in prison, they then still had to cut, and there was a lot of failed ones through that process too. I don't want to spend too much time on this. They did a formulation. It's a slurry, and they used a deflocculant, and it was to help the silicates stay suspended and the heavy oxides to sink, and they applied this to the surface, and it helped give it a leathery surface, the idea being better diffusion for the charred carbon in the ceramic surface. So they were prepping it for that raku firing was what they were doing here. For the raku firing, these are the student slides. This is an inside joke there. Dr. West was one of the mentors, and this is a slide a student did of him. So there's Baylor recreating it with his tongs that he's going to use. So behind him we're in the foundry, it's a furnace. And so what he was going to do is he did a firing with that TerraSig, and then he removed it from the kiln and put it in these metal containers, waited a minute, and then applied the horsehair and pheasant feathers. So a lot of times, if other people have seen raku, it's usually like a lot of organic material, grass, straw, feathers, all these sorts of things, but it gives really cool designs on the clay body itself. For this, they used actually horsehair and pheasant hair. They went out, or feathers, excuse me, and they went and found those. Once again, proper PPE was used for that. And this is their slide. They really wanted to give a shout out to their flautists. and I didn't catch her name. Sam, that's right, Sam Peppel. And so she did a great job. They had gone back and forth with her a couple times, but they were really excited when they were able to hand it off to her. They also had some recommendations. That's usually a common part of design, and kind of wraps up the 2 different design processes. I know I kind of flew through those. Do you want to do it? Or? Let's do questions now and then. Yeah. So thank you guys very much for your time. I think we're going to open it up to questions at this point.
Sure. I'll try and do that without feedback. Okay, so, kind of loud. So over here, this was from the original Foundry project. This is casted. These are casted bells. And they're beautiful. Oh, sorry, backwards. So they're gorgeous on their own, but because our students are so dedicated, it was also a student-designed lyre to hold it. And if you look closely at it, they 3D printed images on it because this was for our special performance. And so that was really great. The trine you heard a little bit from 2024. So unlike the really ugly triangle I made, this was a different idea of a triangle, but with multiple strike points, and so we could get multiple pitches. And so they made a bunch of these. I told them they should start selling them as like wind chimes and cool stuff like that because they're gorgeous. So that was a 2024. The gong up here was this year's, and this was a forging group this year. They also built the frame. And then once you get it warmed up, they built the mallet as well. So we actually ended up liking this gong more. We didn't use their mallet, but we used it more than our commercial one. But there's a great video of them trying to flatten it and driving over it with a car, which did not work, in case you're wondering. This is the symbol from the original, no, this was the 2024 group. So it's a little brighter, and you can look, if you look closely at it, it's actually tuned with all of these pock marks, which is something they do in the industry. You heard about the glockenspiel. We had 3 this year. This one, which was casted, we had one that was ceramic, and we did have a glass glockenspiel that held up great in rehearsals and fell apart during the concert, but that was actually a good thing because it was all that idea of processing and learning. You may have noticed for my musicians in the room, none of these instruments are tuned the way they would normally be tuned. Because of our time constraints, I gave them exactly what pitches I need to play the piece, instead of like the flute needs to play like a normal flute. And that means sometimes I had to change the music to fit what ended up happening. And there was a couple instruments where there was some bells that we just could not get into tune, so I put them in a completely different spot that was in a different key. So there was a lot of this kind of like give and take, but none of this was supposed to be commercial. So this is our glockenspiel out of monster cans. I think it sounds good. And then over here was our drum from 2024. This one's a little hard to hear and play upside down, but they had 2 of these drums and we actually had them on stands that would resonate. So that's why you can't hear them as well now, is because we're on a flat surface, but we were actually to pull them through. And then this guy I love. So my musicians in the room, the Korean folk song medley by Chance. So we were doing that, and this is what they call a steel tongue drum, and it's actually made out of the bottom of 2 propane canisters. So they sliced open the canisters, did a lot of sciencey things that I just like smiled at, and it was really cool. And then the end product was that they could play that main melody. And so again, specific to that piece, but like if I ever start a yoga studio, I'm good. This is my beautiful triangle, which was interesting. This was this was the Carillon Bell testing.
Yeah, this one was fun because the students started out with, yes, a 3D printed design, and then once they put it in the sand, I think this was a sand cast, if I remember, or an investment cast. I don't know, I should make the students in the back that are here come up and talk about it. But that was a casting one, but they used that as their initial one, and we just kind of like that cross section so you guys can see that process. So yeah, and if you come and actually look at this, you can see how the inside or the edges are nice and ground down, so that helps with the sound as well.
These were the hardest for us to tune. We spent many, many hours getting as close. And the other thing is with those apps, they're not really set up for percussion as instruments that resonate at such a different level. And so a lot of time I had them come into the space and we would play the traditional commercial instrument and then against the others and try and find good strike points. And then the last thing are these straight mutes that are on a couple of the tables. That was my bonus gift this year. One of the 3D ceramic team kind of decided to do the flute, which was amazing. And one of our students, Baylor, loved this project so much that he made me 8 of these. And so my entire trumpet section was able to use them. They're ceramic, so don't drop them. As a trumpet player, that's an inside joke because we drop our mutes all the time. But they're a little darker, but a beautiful sound that's really unique, a little bit of pitch stuff. So that's all the ones we had today, but there were other things both for the Foundry project and for the design projects. Good. Any other questions? Ooh. Yeah. Brett.
Yeah, actually the Carillon Bell one, that was super fascinating because they went into the history and they had an awesome picture. What I showed you was the final presentation. They have 2 to 3 presentations kind of throughout the term, so the faculty are pretty well versed in that. But they had the way they used to do these is they would dig out the ground, and it's crazy because there's an old black and white picture of 2 people in the ground, and it's deeper than like their height. So, they were digging those out to do some of these castings. So they do have a lot of history that they dive into and what has been done and what has been done, but what can we do with the facilities, time, money we have. So yeah, that one was a really fun one to see though. Yep. And then I guess this one is kind of another fun story a little bit along that way. This was supposed to be an udu drum, and an udu drum comes around and kind of has this top part. And if you kind of had saw it maybe in the first video where it had started cracking. So they had actually looked into, I think those were from Africa. That sounds right. They had dug into a little bit of that, looked at what is there in clay that would be similar that we could work with as well. So the other thing to add on to that is Dr. Armstrong usually starts the semester off with introducing the problem statement, but she gives them a couple different musical pieces. So she does a really great job on just where are these pieces, where are they located just geographically. So they already start with a little bit of history, and then it's kind of fun to see the students within each of their projects kind of dive into that. Were there any other questions?
All right, well, since we don't have any other extra questions, I will show you a little bit of how this year's projects went. So these are excerpts so this year we did 3 different pieces, so we used the instruments in different ways, and sorry, the video quality isn't the greatest, but the sound is great, and you can kind of see where they're at. So you'll get to see the steel tongue drum in use, you'll get to see all 3 glockenspiels, and then also some of the casted and the lovely gong as well. So give this a listen. So you're going to see him strike the Korean style casted bells here in a minute. Same piece a little bit later. So the gong right there. Xylophone is that one. And then lastly, the steel tongue drum is being added. All right, and this will feature the flute, which I did have to change the instrumentation just so we could hear it, and then also ceramic and the gong. So that's ceramic glockenspiel. All right, so the whole trumpet section there in the back is going to be using these ceramic mutes. And last, this was our glass glockenspiel. It's the first time we've done a glass blowing. Yep. Oh.
We like to break, and what's the other two parts? Yeah, and innovate. But really honestly, we couldn't see that coming. That was the glass marimba, and it did, believe it or not, hold up during our performance during our practice on Wednesday. And I'm actually glad it broke, because this is what college is about, right? Like, you don't have to be perfect. And I'm going to take a moment to say that over and over and over for these students, because a lot of you are their friends and family. I'm guessing they try to be perfect a lot. And this is a place where they should try new things. So yes, I'm sorry, junior design, that one didn't work out, but it's pretty cool what they've created and what they've done.
Yeah. So yes, that one was not as successful, but the great thing is that was the first year we've done anything with glass. And they did an incredible job on the science of it, and so now there's a foundation for future classes. So maybe you'll let us keep being the customer down the road so we can have more fun instruments. Any other questions?
A couple things. One, they did use a couple different sources for their glass, but it didn't ever look like it fully fused. They went and remade a couple of them, and they did a bunch of different strike tests. One of the thoughts was it was against a cold wall. I don't know that that was enough to do it personally. I think it was more of a fusing problem. But I think one of the cool things about the students is sometimes when they hit those roadblocks, instead of giving up, I got more effort out of them after it broke. And they had another 2-3 weeks, and so that it was them going and seeing. We didn't see much differences with the different glasses they looked at. We thought that was one problem. They looked at impurities. I think what it came down to is just full fusion of the piece. So they just didn't have that quite as well. They had done smaller tiles along the way with really good fusing, and then they went to a bigger piece, and they had a lot more challenges with the thermal parts. So that was probably what it was. If you could see the piece, you could see where parts of it hadn't fully fused. It was like only partially fused. So, yeah, we went through a full dress rehearsal, no problems, and I think out of the opening gate it broke. So, yeah, you know, that's part of it. We have, I should probably back up and talk a little bit about our Met Design series. The way we do it is we have our first semester is the second half of junior year. And so they have just a semester of design, and it's kind of high level, covering these different engineering components, problem statement, those types of things. And then the next year is a year-long series we do. So this is it's awesome to be able to work with Dr. Armstrong, because she's great about doing things on the fly, or manipulating the music to align with what we have. Also, nobody got hurt in the breaking of this, right? So this is a safe spot for them to fail and really go and dig back into that design project. So that's one of the nice things I think about this, is it's a little low entry. The stakeholder or customer wasn't that hurt by a failed product in this case. So, yeah. Hey, Larry. 3 to 4. For the glass team, we had 4. For a couple of the other teams, I think most of the other teams, it was 3 members. So we had 7 teams this year. It was a bigger group, so it was good. All metallurgical engineers, yep. And it was fun too. It's amazing the number of students that we get that we usually, before we make the groups, I kind of give them a high level. You're gonna be working with a metal casting or a metal forging or a ceramic clay body or a glass, and we kind of let them see what interests them a little bit. But then we also asked who has any musical background, and it's amazing. I think every year on each team we've been able to place at least one student who did music in high school. They might not do it now at School of Mines, but they definitely did it in high school, so that's pretty cool. It's also very interesting, the large number of students, like even just pulling a class, it was about half the last 2 years that have had some either choir, music, or band. So some background into notes and string theory, those types of things. Were there any other questions? Yes.
Yes and no. The question was, do musicians learn about the engineering behind it? The intro videos that you saw, I play for the students, then I also played it for the audience. So at least they had some idea of the designs and what to listen for, but they didn't go as deep into the science. I think my students would love that. The other neat thing is they're all science engineer types, so the musicians are very invested and supportive, even though this isn't their medium. And the other interesting part is the metallurgical department is not one of our largest. And so it's neat for the other majors in my groups to see and experience what they're going through and the testing. And like we have a day where all the percussionists, we get together and try all their instruments. And so they're really hands-on with it. And then some of them, like Sam, she got dug into the science. She was there along the whole way. So there's a lot of interest that kind of comes up through it, but we don't give them the full science. I'm lucky, I'm the one who gets to sit through the presentations and pretend and learn, and yeah, so if there was enough time, I think that would be a great aspect of it.
And that's a great point. We should actually open it up to the band, the different design talks. I never thought about that. They'd probably enjoy it. Were there other questions? Ooh, I think we're right on time. Thank you all.